Hey everyone, and welcome. Today we're going to peek inside the secret recipe book of modern engineering. We're going to explore the incredible materials that literally build our world, from the phone in your hand to the jets way up in the sky. And we're going to figure out what exactly makes them so special. So let's start with a puzzle. What could a high-performance aircraft and a tiny engine piston possibly have in common? I mean, it seems kind of random, right? One is soaring through the clouds, the other is stuck inside an engine dealing with insane pressure and heat. But believe it or not, they share a deep, fundamental secret. And that secret? Well, it lies in a special family of materials that goes way beyond the classic iron and steel that built our past. We're talking about non-ferrous metals. Now, what does that mean? It's actually super simple. These are just metals where iron isn't the main ingredient. And that one little difference, well, it opens up a whole new universe of possibilities and properties, things like being super lightweight or an amazing conductor. These are going to be the base ingredients in our recipes today. Okay, so our first base ingredient is one you definitely know. Aluminum. It's a foundation for some of the most advanced materials we have. But here's the twist. In its pure form, it actually has a really surprising weakness. So on its own, aluminum has a lot going for it. It's naturally resistant to rust, which is great. It's incredibly light. It's non-toxic. I mean, it sounds perfect, right? But there's always a but, isn't there? On its own, it's actually pretty soft and weak. No way would you want to build an airplane wing out of pure aluminum. And this shows you the core idea of material science perfectly. The real magic happens when you start mixing. By adding just tiny amounts of other elements, we can transform it from something soft into something unbelievably hard and strong. And this is where we get to the really cool part, the secret recipes. We're talking about alloys. And these are not just random mixtures, okay? They are super precise formulas that engineers have perfected over years for very, very specific jobs. So, recipe number 1, duraluminum, and just look how little we have to add. It's just 4% copper and literally a pinch of manganese and magnesium. That's it. And that simple recipe creates a material strong enough for aircraft frames and car parts. It keeps all that great low weight of aluminum, but gives it the muscle it desperately needs. All right, next up, a recipe for when things get hot, yalloy. The secret ingredient here, it's the nickel. See, nickel helps the alloy keep its strength and structure even under extreme heat. And that's exactly why it's perfect for parts like pistons and jet engine heads, where things get seriously, seriously hot. Our final aluminum recipe for today is magnesium. In this one, magnesium is the real star of the show. By tweaking the amount of magnesium, engineers can fine-tune the material's properties for all sorts of different uses in cars and planes. It just drives home that key point. You need different recipes for different problems. Okay, let's clean off our workbench for a second and switch to a brand new base ingredient. We're moving from the king of lightweight strength to the undisputed champion of conductivity, copper. I mean, copper's natural resume is just incredible. It's soft, it's easy to shape. That means it's malleable, so you can hammer it into thin sheets. And it's ductile, meaning you can draw it out into incredibly thin wires. But its superstar quality, the reason it's in basically every electronic device you own, is its absolutely amazing ability to conduct heat and electricity. But just like with aluminum, pure copper is great, but its alloys are legendary. In fact, 2 of its blends are so important that we named entire ages of human history after them. So let's check out the recipes for brass and bronze. First up, we have brass. At its heart, it's a super simple 2-ingredient recipe. Just copper and zinc. But, as any good chef will tell you, the real secret isn't just the ingredients, it's the proportion. So that's the million-dollar question for an engineer, right? To get the absolute best performance, what's the perfect amount of zinc? Is more always better? Well, let's find out. This graph tells the story perfectly. As you add more zinc, the ductility, which is just the ability to stretch the metal without it breaking, it goes up and up and up until it hits this perfect peak right around 37%. If you add any more zinc after that, it actually starts to get weaker. That 37%, that is the sweet spot, the perfect recipe for making it as stretchy as possible. And you can keep refining the recipe. You can add even more things. Need it to be easier to cut and shape with a machine? Just add a little lead. Need it to be even stronger? Throw in some tin. It is all about customizing the material to get the job done. All right, now for copper's other world-famous partner, bronze. This time, we're mixing copper with tin. And what tin brings to the party is a really crucial property, hardness. And that brings us to a classic recipe, gunmetal. Now, it's mostly copper and tin, but did you notice that little 2% of zinc in there? That's not for strength. It's actually added as a deoxidizer. Think of it like a tiny cleaning agent that gets rid of impurities while the metal is being melted, which stops it from becoming brittle. So it was originally designed for making cannons, but today we use it for really durable parts like boiler fittings that have to be super tough and reliable. So when you step back and look at all these recipes, this really powerful idea starts to emerge. We've moved way past just, digging materials out of the ground and using them as they are. We are truly in an age of material design. And this is the main takeaway. We have entered an age of modern alchemy. Engineers are like master chefs, precisely combining elements from the periodic table to cook up brand new materials with the exact properties they need to solve a problem, whether that's building a lighter airplane or a more efficient engine. And all of this leaves us with one final, huge question. We've had the Stone Age, the Bronze Age, the Iron Age. As we keep designing these new recipes, right down at the atomic level, what material, or maybe what family of materials, is going to define the era that we're heading into right now?